Welcome back to QHSE Talks, where safety is approached as a living risk system, not a collection of procedures. Construction does not operate inside stable conditions. It functions inside environments that shift, reorganize, and transform as the work progresses. Space changes, structures develop, loads relocate, energy moves, access evolves, control measures adapt. Human decisions respond under pressure. Risk does not stay in one place. It travels with the work. That reality explains why construction remains one of the highest fatality industries across global safety data. Not because regulations are absent, not because standards are unclear, not because training is unavailable, but because construction is an industry where the process itself reshapes the hazard landscape. Progress changes the system. Change creates exposure. Exposure increases consequence. Chapter 25 is built around that reality. It does not treat construction as a compliance problem. It treats it as a dynamic risk system. And from a professional certification perspective, this is exactly where it aligns with the CSP-11 Blueprint. It reflects Domain 1, advanced application of safety principles through applied hazard systems, not theoretical models. Ground failure mechanics, electrical energy behavior, fall force dynamics, mechanical lifting systems, welding hazards, and tool-generated kinetic energy. It also connects directly to Domain 6, occupational health and applied science, where harm is not always visible. Airborne contaminants, toxic metal fumes, ventilation breakdowns, hot work atmospheres, oxygen displacement, and long-term physiological exposure. This integration matters because construction risk is never isolated. Physical danger overlaps with health exposure. Mechanical systems intersect with human judgment. Environmental instability interacts with decision-making under pressure. So this episode is not about rules. It is about risk formation. How danger develops, how systems interact, how normal operations generate abnormal outcomes, how familiar environments produce extreme consequences. This is the professional mindset Chapter 25 is designed to build, a way of thinking that views the job site not as a location, but as a moving risk environment. And that is why the chapter begins in the place most often misunderstood on a construction site, the ground. It looks stable, it feels permanent, it appears harmless, it inspires false confidence. Yet beneath that surface lies one of the most destructive force systems in the industry.
Let's start at the bottom. Literally, segment 1, excavation and trenching.
The silent killer. That is how it is often described.
It is deceptive. I think for the layperson or even a rookie safety officer, there is a tendency to underestimate dirt. It's just soil. It's been there forever. We played in it as kids. Why is it suddenly a mortal hazard just because we moved some of it?
It comes down to two things: weight and coherence. The source material emphasizes this really heavily. Soil is a fluid that thinks it is a solid.
A fluid that thinks it's a solid. I like that.
Yeah. When you cut a trench, you are removing the lateral support that was holding that wall of dirt up. Gravity immediately goes to work trying to pull it down to a stable angle.
And the text gives a comparison that, it really sticks with you regarding the weight.
A cubic yard of soil. Picture a box, 3 feet by 3 feet by 3 feet. That box of dirt can weigh as much as a compact car, somewhere between 2,500 and 3,000 pounds.
3,000 pounds.
Depending on the moisture content.
So if a trench wall collapses,
Yeah.
it isn't like being buried in sand at the beach. It is like having a Toyota Corolla dropped on your chest from vertical.
Exactly. And the cave-in hazard described in the chapter, it isn't a slow process. It's not like the movies where you hear a rumble, see some pebbles fall, and you have time to scramble out.
Right, you get a warning.
There's no warning. The test describes it as instantaneous. The soil shears away, and because of that immense weight, the impact force is just massive.
So even if your head is above the dirt?
Even if your head is above the dirt, the pressure on your torso is so great that you can't expand your chest to breathe. You literally suffocate while looking at the sky.
That is a sobering image. So we don't rely on luck or fast reflexes. The text outlines 3 specific protective systems: slipping, shoring, and shielding. I want to get into the weeds here because the exam questions on this can be tricky, and the real-world application is, well, it's critical. Let's start with sloping.
Sloping is the most basic engineering solution. It is essentially geometry. You are cutting the trench walls back at an angle inclined away from the excavation so that gravity can't pull them down. You're finding the angle of repose.
But you can't just eyeball it and say, yeah, that looks safe to me. The text makes it very clear that the angle depends entirely on the soil classification.
Oh, absolutely. You have to know what you're digging in. You have type A, type B, and type C soil. And this is a hierarchy of stability.
Okay, walk us through those. What's type A?
Type A is your best case scenario.
Yeah.
It's cohesive, clay-heavy soil. It has high, unconfined compressive strength. Basically, it sticks together. Because it is stronger, you can slope it at a steeper angle, 34:1, or about 53 degrees. It holds its shape better.
Then you have type B. What's that like?
Type B is less cohesive. Maybe it's angular gravel or silt, something a bit looser. It's not terrible, but it's not solid clay. You have to slope that back to a 1-to-1 ratio, so 45 degrees.
And then type C.
Type C is the dangerous stuff. Granular soil, sand, or any soil that's submerged in water. It has basically zero cohesion. It's like trying to dig a hole in a pile of sugar. It just wants to flow right back into the hole.
Right.
For type C, the slope has to be incredibly flat, 1.5-to-1. That means for every 1 foot of depth, you have to cut back 1.5 feet horizontally.
So if you have a 10-foot deep trench in sandy soil, you're cutting back 15 feet on each side.
On each side.
That is a 30-foot wide chasm just to lay a small pipe.
Exactly. And that is the problem in the real world. In an open field, sloping is great. But in a city street, or right next to an existing building foundation, you don't have the real estate to slope back 30 feet.
Which brings us to the second system, shoring.
Right. Shoring is about resistance. If sloping is removing the weight, shoring is fighting the weight.
Okay, and this involves installing supports aluminum hydraulics, timber, pneumatic systems.
Think of it like bracing a door frame, but on a massive scale. You are inserting a structure into the trench that physically pushes back against the walls. It creates an opposing force that is greater than or equal to the pressure of the soil. It's proactive. It stops the movement before it starts.
Okay, so sloping removes the hazard. Shoring braces the hazard. That brings us to the third one, and this is one I see all the time on roadsides, shields or trench boxes.
Right, and there is a critical distinction here that the text makes, and it is a nuance that often trips people up on exams.
Okay, what's that?
Trench boxes are designed to protect the worker in case of a collapse, not necessarily to prevent the collapse.
Oh, interesting. So the walls could still cave in.
Technically, yes.
Where?
Ideally, you don't want that to happen, but the primary function of the shield is to create a safe haven. Imagine a big steel cage. You drop it into the hole. The worker stands inside the cage. If the walls of the trench collapse, the dirt hits the outside of the steel box. The worker inside survives.
It's like a shark cage for dirt.
That is a very apt visual, a perfect analogy. And the text notes that you often see these used in combination. You might slope the top of the trench and use a box at the bottom. But the key takeaway for the listener is that difference in philosophy. Shoring supports the wall, shielding supports the worker.
Got it. And there was one more acronym mentioned in this section, RPE.
Yes, Registered Professional Engineer.
So when do they get involved?
The text mentions that for complex excavations, or specifically excavations over 20 feet deep, you cannot just use the standard OSHA charts or the manufacturer's tabulated data.
Why is 20 feet the magic number?
It all comes down to lithostatic pressure. At that depth, the weight of the earth is so immense and the variables become so complex, groundwater, different soil layers, that standard charts just aren't safe anymore.
So you need a custom solution.
You need a system designed specifically for that hole in that soil, stamped by a registered professional engineer. You just don't guess with gravity at 20 feet.
Got it. Under 20 feet, follow the charts and soil types. Over 20 feet, call the engineer.
Precisely.
All right, let's climb out of the trench and look at something that is essentially invisible but equally deadly. Segment 2, invisible energy electrical hazards.
Always a top killer in construction. Always.
The text lists the big threats, shock, fire, and explosions. And it highlights the specific controls we expect. De-energizing equipment, LO2PO, a lockout tagout, keeping your distance from power lines, all the standard stuff. But there was a section here that I found really fascinating because it dealt with something we usually consider a minor annoyance. Static electricity.
It does, and for good reason. In the general world, static electricity is a nuisance. You walk across a carpet, you touch a doorknob, you get a little zap. No big deal.
Right.
But on a construction site, you are often dealing with fuel transfers, solvents, fine dusts, flammable vapors. In that environment, a little zap is an ignition source. It's a spark. And a spark can lead to a catastrophic explosion.
So how do we control a spark that naturally builds up just from moving fluids or materials? The text lists two critical methods, bonding and grounding. And I have to be honest, before reading this chapter, I use those terms pretty interchangeably.
Most people do. It's a very common point of confusion. But they are physically different mechanisms performing very different functions.
Let's break them down. Bonding first. What is it?
Okay, let's look at the physics. Bonding is connecting two conductive objects together with a wire. For example, you have a fuel truck and you have a metal drum you are filling. Both of those metal objects can build up their own electrical charge. If the truck is at, say, 100 volts of potential and the drum is at 0 volts, and you bring the nozzle close,
The electricity jumps. You get a spark.
you get an arc. Spark. Boom. Bonding is simply running a wire, a conductor, between the truck and the drum.
And what does that actually do on an electrical level?
It equalizes the electrical potential between them. Think of it like water levels. If you have 2 buckets of water connected by a pipe at the bottom, the water level will equalize. It's the same principle. If 2 objects are bonded, they share the same electrical charge.
So if they have the same charge, electricity doesn't want to jump from one to the other. There's no difference to equalize.
Exactly. A spark is electricity jumping across a gap to equalize a difference. If you bond them, you eliminate the difference. So essentially, they are shaking hands electrically. I'm at this level, you're at this level, let's just agree to be the same.
I love that. Bonding is an electrical handshake.
Yeah.
So then what is grounding? How is that different?
Grounding is connecting the object directly to the Earth.
To the planet itself.
To the planet. The Earth is, for all practical purposes, a massive reservoir for electrons. It has 0 potential. When you ground an object, drive a copper rod into the dirt and wire the truck to it, you are providing a path for any charge to leave the object and go harmlessly into the ground.
So bonding equalizes the two objects so they don't spark at each other, but grounding actually drains the charge away entirely.
That is the takeaway. That's the perfect way to put it. Bonding connects things to each other. Grounding connects things to the planet. Ideally, during a fuel transfer, you do both. But for the exam candidate listening, remembering that distinction is vital.
That is really helpful. Bonding connects things. Grounding connects to the earth. Okay, moving on. We've dealt with the ground. We've dealt with energy. Now let's talk about one of the most persistent forces in nature, gravity. Segment 3 is all about fall prevention versus fall protection.
Another area where terminology matters immensely.
Again, these are terms I used to swap around all the time. But the text treats them as distinct philosophies with a very clear hierarchy.
They are absolutely distinct philosophies. And the hierarchy is based purely on effectiveness. Fall prevention is the gold standard.
Define it for us using the examples in the source. What is prevention?
Prevention means stopping the fall from happening in the first place. You are modifying the environment so the hazard is, inaccessible. Examples would be guardrails. If you put up a sturdy rail, the worker cannot physically fall over the edge.
Right.
Warning lines that keep people back 6 feet from the edge. Controlled access zones. These are all passive systems.
Passive meaning the worker doesn't have to do anything for them to work. They don't have to clip in or anything.
Exactly. The rail works whether the worker is paying attention or not. It just exists.
Okay. Contrast that with fall protection.
Fall protection assumes the fall will happen, or at least that it can happen, and plans for catching the person after the fact.
So this is the parachute approach.
Exactly. Personal fall arrest systems, your harness and lanyard, safety nets. These don't stop you from tripping and falling off the beam. They just stop you from hitting the ground.
And the expert view here, and the text supports this, is that prevention is always superior to protection.
Always. I mean, think about it. Even if the harness works perfectly, falling is traumatic. You swing, you can hit structures on the way down. The psychological shock is massive. Prevention removes the event entirely.
Sure.
But obviously in construction, you can't always put a rail up on a steel beam 40 stories up while you're building it. So protection is necessary.
Speaking of protection, the text goes into some really deep detail on safety nets. It felt like I was reading an engineering manual for a moment there.
It is very specific.
Yeah.
And for good reason. If a net fails, it's catastrophic. There's no backup.
It mentioned a drop test. Tell me about that.
Yes, you can't just hang a net and hope it works.
Uh-huh.
The text specifies a validation test using a 400-pound bag of sand.
400 pounds. But the average worker isn't 400 pounds?
No, but you aren't just catching static weight. You are catching dynamic force. Force equals mass times acceleration. A 200-pound worker falling 10 feet generates thousands of pounds of impact force. The 400-pound sandbag drop simulates that shock load to ensure the net and its anchors won't rip out of the concrete.
And it's not just about strength, is it? The text highlights clearance. This is something people forget. Nets stretch. They are elastic. If you fall into a net, it might sag 5 or 6 feet. So if the net is hung only 3 feet above the ground,
You hit the ground. The net catches you, but the ground stops you. You still get injured. So the text emphasizes that there must be sufficient clearance below the net, so the falling person doesn't strike the surface below while the net is stretching.
it's those details that save lives. It's not enough to buy the net. You have to do the math on the clearance.
Precisely.
Now, this leads us directly into what I think is the most terrifying and perhaps the most educational part of this chapter. Segment 4, suspension trauma.
This is the aha moment for a lot of people. It fundamentally changes how they view fall protection.
So paint the scenario for us. A worker falls. They are wearing their personal fall rest system, the harness, the lanyard. It works perfectly. They don't hit the ground. They're just hanging there, suspended in midair, waiting for the fire department. They are safe, right?
That is the assumption. The harness saved me. But the text reveals a dark reality. Being suspended in a harness, immobile, can kill you in under 10 minutes.
Under 10 minutes. That is faster than most ambulance response times in a city.
It is. And to understand why, we have to look at the physiology described in the text. It's called orthostatic intolerance.
Right. Let's break down the mechanism. What is happening in the body when you're just hanging there?
Okay, so normally when you are standing up or walking, your leg muscles are contracting. Every time they squeeze, they pump blood back up your veins, fighting gravity to return it to your heart. The legs are basically a second heart.
Got it. The muscle pump.
The muscle pump. When you fall and hang in a harness, your legs are just dangling. You aren't walking, you are immobile. The straps are tightening around your thighs, constricting the veins. Gravity pulls the blood down into your legs, but there is no muscle pump to push it back up. This is called venous pooling.
So the blood gets stuck in your legs, a large volume of it.
Massive amounts of it, which means your heart runs out of blood to pump to your brain.
And usually if your brain runs out of blood, you faint.
Yeah.
Right? You fall down, you get horizontal, and blood flow is restored to the brain.
That is the body's natural safety switch. Fainting gets you horizontal. But here is the trap. In a harness, you can't fall horizontal. The harness holds you upright.
Oh, wow. So the brain triggers the faint to save itself, but the equipment forces you to stay in the very position that is killing you.
Exactly. You pass out, you stay upright, the brain loses oxygen completely, the airway restricts, and death occurs. It is a silent, rapid killer.
That is terrifying. But then the text introduces another layer to this nightmare. It's called reflow syndrome.
This answers the question. Okay, we rescued him, we got him down, let's cut him down.
Right. Get him down, lay him flat, let him recover, standard first aid.
If you do that, you might kill him.
Wait, really? Laying someone flat is standard first aid for shock.
Not for this. The text mentions reflow syndrome. Think about that blood trapped in the legs. It's been sitting there for maybe 10 or 15 minutes. It is now stale.
Stale.
The cells have used up all the oxygen. It is saturated with CO2. It is filled with toxic metabolic waste products like lactic acid and potassium.
It's practically poison.
It is toxic blood. If you rescue the worker and immediately lay them flat on a stretcher, gravity aids the flow, and all of that toxic blood rushes back to the heart and brain all at once.
It creates a massive shock to the system.
It can stop the heart instantly. It's called reperfusion injury, a sudden cardiac arrest.
So the rescue protocol in the text is very, very specific about this.
Extremely specific. First, time is critical. Rescue must happen within 10 minutes. You cannot wait for 9/11. You need a site rescue plan.
And the post-rescue position. What do you do once they're on the ground?
Do not lay them flat. The text advises keeping them in a sitting position, knees up like a W position, for at least 30 minutes.
To allow the blood to trickle back slowly.
Exactly. You want to reintroduce that blood to the core of the body gradually so the liver and kidneys can filter it rather than flooding the engine with bad fuel all at once.
That is a life-saving piece of information. If you take nothing else from this deep dive, remember that. Don't lay a suspended victim flat immediately.
Now, what about the worker who's hanging there? Is there anything they can do while they wait?
Yes. The text lists self-rescue techniques. The goal is to keep that muscle pump working, even a little bit.
So just moving the legs.
Pumping the legs. straining the muscles every 5 seconds. If the harness has trauma straps, little loops you can deploy to stand on, use them immediately. Anything to push against, to flex those muscles and send blood upstairs. And of course, calm breathing to conserve oxygen.
Incredible. It really shifts your perspective from the fall is the danger to the suspension is the danger. It's a completely different medical emergency that starts the second the fall is arrested.
Let's move on to our final segment before we wrap up. Segment 5, specific site hazards. We're talking concrete, masonry, and tools.
These are often the hazards that get overlooked because they seem mundane compared to falling 40 feet, but they are just as vicious.
The text mentions concrete and masonry specifically. What stood out to you there?
Impalement.
Oof, yeah.
Construction sites are full of vertical reinforcing steel rebar. If you trip and fall onto an uncapped piece of rebar, well, the physics are gruesome. The text is very clear. Rebar needs capping, and not just with a flimsy piece of mushroom plastic.
I see those little orange caps all the time. Are those enough?
Only if they are steel reinforced. The cap needs to be flat and strong enough to stop a body from being pierced. A cheap plastic cap will just become part of the wound.
It also mentions cement, dust, and silica.
Which brings us back to chemistry. Wet concrete can cause severe chemical burns because it's so alkaline. But the dust silica is a major respiratory hazard. If you are cutting concrete without water or a vacuum, you are creating a cloud of microscopic glass shards. The text equates the long-term risk to asbestos.
And post-tensioning operations, what's that about?
Post-tensioning. Yeah, these are high-energy cables used to strengthen concrete. They use hydraulic jacks to tighten these steel cables to incredible tension. If one of those snaps or the jack fails, that cable acts like a whip that can cut through just about anything. It's stored energy, similar to the electrical hazards we discussed earlier.
And finally, tools and equipment.
Simple things, really. Inspecting cords. Are they frayed? Using guards on grinders. You'd be amazed how many people take the guard off a grinder to get a better angle, exposing themselves to an exploding disc. And the text specifically mentions lockout to gout in the construction context.
Usually we hear oloto in factories on fixed machinery.
Right, but the text makes the point that it applies here too. If you are servicing a generator, a concrete mixer, or a chop saw, you have to lock it out. Just unplugging it isn't always enough if someone else can walk by and plug it back in without you knowing.
It all comes back to respecting the energy, doesn't it? Whether it's kinetic energy in a spinning blade or electrical energy in a cord or potential energy in a high-tension cable.
That is the common thread through this entire chapter.
So we have covered a lot of ground today. We went from the mechanics of soil collapse and excavations to the physics of bonding and grounding electrical charges. We looked at the hierarchy of fall prevention versus protection, and we took a really sobering look at the biology of suspension trauma.
It really is a journey through physics, chemistry, and biology, all on one job site.
If we had to synthesize this for the listener, maybe they are prepping for that CSP exam, or maybe they just want to be safer on site, what is the core takeaway?
I think the core philosophy is that construction safety isn't just about following rules or checking boxes. It's about understanding the forces of nature. Gravity doesn't care if you've been on the job for 20 years. Electricity doesn't care if you're just checking one thing. Soil doesn't care if it's just a shallow trench.
You have to respect the forces.
You have to respect them. For the exam candidate listening, remember the distinctions we talked about: bonding versus grounding, prevention versus protection, and that 10-minute window for suspension trauma. Those are the technical details that matter.
And for the general learner, for someone just driving by a site.
Next time you walk past a construction site, look for the trench boxes, look for the harnesses. You now know the science, keeping those workers alive. It gives you a new appreciation for the engineering that goes into safety.
Absolutely. Now, before we sign off, we always like to leave you with a provocative thought, something to chew on.
This one comes from that discussion on suspension trauma. We talked about how reflow syndrome is medically complicated and how rescue can sometimes be fatal if done wrong, laying them flat, for example.
Right.
It raises a difficult question. Are our rescue plans as robust as our fall protection plans? It is relatively easy to buy a harness. You go to the store, you buy it, you check the box, you put it on. Compliance achieved. But planning the rescue, training the team to get someone down in under 10 minutes, ensuring the ambulance crew that arrives knows about reflow syndrome. That is where the real work is.
Buying the gear is the easy part. Planning the survival is the hard part.
Exactly. A harness without a rescue plan isn't a safety system. It's just a way to leave someone hanging.
Powerful stuff. That's it for this deep dive into Chapter 25. Stay safe out there, respect the physics, and we'll catch you on the next one.
Stay safe.